All right, so we're going to take that same exact equation, and we're on section 5.0, and we're going to take the same equation we just had. So any heat that I add into a process plus any energy that was already existing in the working fluid on that process must equal any energy that's left over after something occurs plus any work. And we see that I use Joule's constant to equate the two. Work here needed to be converted to BTUs. And that's why we use Joule's constant there. Now what we're going to do is we're going to try and create a general energy equation by doing exactly what I told you we were going to do and figure out what the energy's type could be, what form of energy this is. So we'll see that Qn, this is just a different way of looking at everything, must equal the different energies. Well, that's potential energy plus kinetic energy plus PV energy plus internal energy. And all of these energies were the work in, just the different forms that they could have taken, must equal, well, all those energies again, potential energy plus kinetic energy plus PV energy plus internal energy, and this is all out, plus the work that I extracted. And I ran off the boards right over here, so you can see I'm kind of curling it around. Plus work. So sometimes there's a sign convention. So like if I was to apply this general energy equation, and I'll rewrite it so we can see it all the way from left to right, and it'll just take a sec here. So heat that I add plus potential energy plus kinetic energy plus PV energy plus internal energy equals potential energy plus kinetic energy plus PV energy plus internal energy plus work. That's just rewriting this equation up here. Now, I mean, we can subtract all of these and put them on this side and set this to 0. And this would be the change in potential energy plus the change in kinetic energy plus the change in PV energy plus the change in internal energy plus heat that I add minus the work that I do must equal 0. We could do that. Get rid of that right there. So we've just set it equal to 0 by subtracting this entire side of the equation. And on your equation sheet for the NRC exam, that's what Bernoulli's equation does for you. So if you're following along, I'll show you how to kind of make that a whole lot easier, because it is on the bottom of this page. We can see it, and I'll write it out differently, but we can see the form of Bernoulli's that's getting set to 0 down here, and they're actually just going to do some substitution, essentially. So if I have the change in potential energy, that would be the difference in height, where height was Z. There's Z2 minus Z1. That's the difference in height. And if you'll recall, we have to go G divided by G sub C. And that really just helps us with our units. And then the other energy, this was potential energy. So there's the change in potential energy due to height. The change in kinetic energy. Well, there's one little thing you got to remember here. That's the change in velocity, but these were between in and out. I used 2. This is 0.2, and this is 1. So this would be the kinetic energy. So it was the velocity squared, though, you have to recall. So velocity squared 2 minus velocity squared 1 divided by 2 times the gravitational constant. That was the change in kinetic energy. Plus, when we look at, and we're going to introduce this for the very first time, when I look at pressure and specific volume plus specific internal energy, we can call that specific enthalpy. It's a convenient grouping. And it kind of jumped the gun here when we do that. That's how come on your equation sheet you'll see H2 minus H1. That's the change in enthalpy, or the change in pressure, volume, change in internal energy. And then you'll see plus, and this should be in parentheses for understanding, Q minus W equals 0. That is taking all of these energies and this work and subtracting them and putting them over here and saying that the energies could be potential energy, kinetic energy, this being pressure, volume, and internal energy, which is called enthalpy. And we're going to get a lot of work with this term right here because this is key term and understanding what it means. It is the pressure, volume, and internal relationship, or properties rather, of our water / steam. So this becomes the equation that we're going to apply to everything, every process in our plant. Let's apply that real quick, just as kind of a heads up, and see what we're going to do. If I took that equation in its simplest form, that's upper left on section 5.0, and I said, okay, my working fluid can have these following types of energy. And I could add heat to it, where Q is adding heat, is equal to, well, when it's all done with that process, it's going to have some forms of energy, and I may have done some work. But what I started with and what I ended with are going to be the same, but they may be altered in form. So let's take the reactor, and it is nothing more than for our purposes, it's a variable heating element. And I know that feed water comes in at a certain temperature, and let's just assume it comes in at 400 degrees Fahrenheit as water. And I'm going to use a term here, subcooled water, and let's say it leaves as steam. This is steam and this is water. Well, most of us understand what happened here. The water came in, got heated up, then it started to boil and steam left the reactor. Well, if I was to now see how I changed the energy of the fluid, which is water, what did I do? Did I change the energy due to a change in height here? Well, the height is the difference between the feed water inlet and the steam outlet. And we already know that 1 BTU is 778 feet-pounds force. So if I said, no, I don't think we add energy by raising its potential energy, I don't think it would be much of a leap here to say we can omit the potential energy terms in this process. How about this? Do I have a huge change in velocity between the feed water in and the feed water out? And the answer once again is nope, we're not actually trying to raise the energy of the working fluid by raising its velocity. When we come down to kinetic energy, they're gone. Is this reactor, is there something spinning in it? Or is it just a heating element? Well, the answer is obvious. It's not a spinning piece of equipment. Spinning is work. So there's no work done in this right here. What's left is the Q of this reactor, the heat that this reactor adds, energy in the form of heat that it adds to the working fluid. And we see that it is this and this. And so I'm going to subtract this PV plus U here to both sides. And this is in, and this is out. So you can see that the Q of my reactor, the energy that I add to the working fluid, this is essentially the heat rate. This is heat added per unit time, and we'll get to that. But it is equal to the energy of the steam minus the energy of the feed water that was coming in. So I look at the pressure-volume relationship between the two, and this is the outlet, steam, which has a high enthalpy, high energy, minus what came in from the feed water. And we'll be doing this a lot in topic number 4. So we're going to call this enthalpy out minus enthalpy in. So it's just, what did it do to water? Well, it raised the pressure and internal energy of the water. And the difference between the two, the change in enthalpy, was the outlet enthalpy of the steam minus the inlet enthalpy of the feed. So we're going to be doing that a lot in topic 4.